You know, when you grab a plastic bottle or see the tires on a car, you probably don't think they have much in common. But they do. They're connected by this incredible chemical process that literally builds the world around us. And today, we're going to pull back the curtain on that secret.
So let's start with a little riddle. What in the world does a plastic water bottle, a heavy-duty car tire, and your super soft fleece jacket all have in common? I mean, they look different, they feel different, they have totally different jobs, but underneath it all, they share the exact same chemical secret.
And that secret is polymerization. It sounds complicated, but it's really just the process of taking tons of tiny little molecules, called monomers, and linking them up into these massive long chains called polymers. That's it. That's the answer to the riddle, and that's what we're diving into today.
All right, so here's the game plan. First, we're going to get a really clear idea of what polymers are. Then we'll check out the three main ways chemists cook them up. And finally, we'll see how these invisible chains are just, well, they're everywhere.
Okay, first things first. What exactly is a polymer?
The best way to think about it is with paper clips. Seriously. Imagine you have a single paper clip. That's your monomer. Now, what happens when you start linking them together, one after another, into a super long chain? Boom, you've just made a polymer. It's that simple idea of linking small things into one giant thing. So, if monomers are paper clips, how do we actually link them? Well, our first method is all about using special connectors, or what scientists call functional groups.
For this one, let's switch from paper clips to Legos. Imagine you have a pile of red bricks and a pile of blue bricks. And the rule is, a red brick can only snap onto a blue one, and a blue one can only snap onto a red one. They can't connect to their own color. That's the core idea here, using two different types of monomers that are made to connect only with each other.
So here's how it plays out. You've got your two different monomers, and they each have these special reactive ends. They get close, those ends find each other, and snap! They form a new bond. And here's a cool little detail. When they link up, a tiny molecule, usually just water, gets kicked out. This happens again and again, building the chain piece by piece. And this step-by-step method gives us some amazing materials. That polyester shirt you're wearing? Yep. The super strong nylon and ropes and tents? You bet. And get this, even Kevlar, the stuff in body armor, is made this way. The reason it's so incredibly strong is because this specific process lets those polymer chains line up perfectly, creating a material that's literally stronger than steel. How cool is that?
Okay, method number 2 is a whole different ballgame. We're leaving the careful step-by-step process behind. This one is all about speed, a rapid-fire, unstoppable chain reaction.
The perfect way to picture this is a domino rally. You just have to tip that first one and the whole line just goes whoosh. This reaction uses monomers that have a special kind of high-energy bond that's just waiting to pop open. Once you pop the first one, it sets off a lightning-fast cascade.
So it all kicks off with something called an initiator. Think of it like the finger that pushes the first domino. It taps that first monomer, breaking open its special bond and making it super reactive. That newly activated monomer immediately grabs the next one, which grabs the next one, and on it goes. The chain just explodes in length, adding thousands of monomers in a flash. You see the results of this domino effect everywhere. You know those white PVC pipes used for plumbing? That's a chain reaction polymer. So is the polystyrene that makes styrofoam cups and packaging. Even a lot of the synthetic rubbers that go into car tires are made with this super fast method. All right, on to our third and final method. And this one starts from a really interesting place. Forget individual building blocks. For this, we start with circles. Yeah, this one totally flips the script. Our monomers aren't just floating around as individual pieces. They're already connected to themselves in these stable little rings. So if you want to build a long chain, what do you have to do first? You got to break the ring.
So here's the magic. An initiator molecule comes in and basically snips one of those rings open. Suddenly, that closed loop pops open into a short chain with a reactive end. And what does that new chain do? It goes and attacks another ring, opening it up and adding it to its own length. It's a chain reaction of rings popping open and linking up end to end.
The stuff we make this way is just fascinating. Nylon 6, which you'll find in carpets and textiles, is a classic example. But so are some really high-tech biodegradable polyesters, the kind they use for medical stitches that just dissolve in your body over time. And that flexible, rubbery silicone in your kitchen spatula or the sealant around your tub, that's a ring-opening polymer too.
So there we have it. 3 totally different strategies for building these incredible molecular chains. Let's zoom out and look at the big picture.
So we've got the methodical, step-by-step linking that gives us polyester, we have that super fast domino rally that makes PVC, and we have the clever break-the-circle method that builds things like nylon 6. It's like having 3 different recipes that can create thousands of different materials. And the scale here is it's mind-boggling. Get this, these reactions are the foundation for over 80% of the entire modern chemical industry. Just let that sink in. The huge majority of all chemical manufacturing is about one thing: making these long polymer chains. So what's the bottom line? Why does this all matter? It's because if you understand these 3 basic chemical recipes, you understand where most of the materials in our modern world come from. From the simplest plastic bag to the most advanced composite, it all boils down to linking tiny molecules into giant chains. You know, it's really no exaggeration. People talk about the Stone Age or the Iron Age, but we are truly living in the polymer age. Our world is literally built out of these incredible giant molecules. And that leaves us with one final, pretty exciting question. We've figured out how to be master builders at the molecular level, so what's next? What kind of amazing new materials, smarter, stronger, maybe even self-healing, are we going to build with these same fundamental rules? The future is being built as we speak, one monomer at a time. Thanks so much for tuning in.